The European engine is a work of art capable of devouring highways, but that perfection has a dark side, the fragility of details. While engineers in Stuttgart obsess over extreme performance, they sacrifice the durability of the everyday. Congratulations, you have bought a technical prodigy whose electronics have the resistance of a glass. Today we break down the 14 reasons why these luxury machines live in a love-hate relationship with the workshop. Watch out for position 6 because it explains why a simple plastic can ruin your month. Let us start. Reason 14. The use of biodegradable plastics in the engine compartment. One of the quietest and most devastating causes of long-term unreliability in European vehicles is, ironically, their commitment to the environment. Since the end of the 1990s, the European Union has imposed extremely strict regulations on the recyclability of vehicular components. This has led manufacturers to replace high-resistance plastics and petroleum-derived polymers with compounds that include organic and biodegradable materials. The problem lies in the fact that the engine compartment of a modern car is a hostile environment, a thermal torture chamber where temperatures fluctuate constantly between 10 degrees below zero and 110 degrees Celsius. Under this constant cycle of thermal expansion and contraction, these ecological plastics begin a process of accelerated degradation. Critical parts such as cooling system flanges, electrical connector housings, and timing chain guides become brittle, acquiring the consistency of a dry cracker. While in a Japanese car from the same era these components can retain some elasticity after 15 years, in a European vehicle it is common for them to pulverize under the slightest pressure from a tool. This pursuit of the green life cycle has created a programmed obsolescence that not only affects the owner's pocket, but generates chain failures, where a simple €5 plastic part that breaks can cause overheating that destroys a €10,000 engine. Reason 13. The excessive complexity of vacuum systems and emissions management. The European obsession with efficiency and the reduction of polluting particles has led to the creation of technological labyrinths under the hood. To comply with Euro 6 and later regulations, engineers have had to implement air and emissions management systems of amazing complexity. We are talking about networks of vacuum pipes, electronically controlled exhaust gas recirculation valves, and crankcase ventilation systems that look like they came out of a space propulsion laboratory. The problem with this architecture is that it introduces a huge number of potential failure points. In these systems, a micro crack in a rubber hose hidden behind the intake manifold is enough to confuse the engine control unit, causing jerking, loss of power, or the dreaded emergency mode. Detecting these faults is a nightmare for mechanics, often requiring hours of diagnosis with smoke machines and computerized analysis equipment. While other manufacturers opt for more robust and simplified solutions, the European approach is to add more layers of technology to correct the problems of the previous layer, creating a mechanical ecosystem where the statistical probability of something failing increases exponentially with each new component added. Reason 12. German sensors and extreme sensitivity to voltage variations. High-end vehicles from Europe operate with extremely narrow tolerance margins. This is critically reflected in their electrical architecture. A mass airflow sensor, or a German-made camshaft position sensor, is an instrument of absolute precision, capable of sending readings with amazing fidelity. However, this precision comes at a price: intolerance. In most European cars, electronic systems are designed to operate within a very specific voltage range. If the battery begins to age and its voltage drops just half a volt below the ideal during starting, the vehicle's communication network, known as the CAN bus, can begin to generate ghost error codes. It is common for an owner to see fault warnings in the anti-lock braking system, the transmission, or the stability control, when in reality the only problem is a battery that is at 80% of its capacity. This extreme sensitivity makes maintenance much more demanding. It is not just that parts break, but that the car's computer system is so strict that any minor fluctuation is interpreted as a catastrophic failure, forcing the user to visit the workshop for problems that, in other vehicles, would not even be detected by the onboard computer. Reason 11. Over-engineering in simple mechanisms. There is a concept in the industry known as over-engineering, and no one practices it with as much passion as European manufacturers. The desire to offer a superior user experience leads to converting traditionally simple mechanisms into complex and motorized systems. A perfect example is electric windows and central locking. While most of the world uses actuators and steel cables proven for decades, a European brand may decide to use a plastic pulley system reinforced with integrated micro-switches to detect the exact pressure of the glass and prevent entrapment with a precision of millimeters. While this brings a feeling of refinement and safety unmatched when the car is new, as the years go by, material fatigue causes these systems to fail with unusual frequency. The result is that the owner is left with a window down in the middle of a storm, or a door that does not close because a small plastic gear inside a sealed module has worn out. This mentality extends to retractable cup holders, motorized air vents, and memory mirrors. Motors and computer logic are added to elements that did not need them, multiplying the possibilities of a small breakdown, ruining the luxury experience. Reason 10. Gaskets and oil seals and the search for absolute tightness. European engines usually operate at higher internal pressures and temperatures than simpler, naturally aspirated engines. To contain fluids under these conditions, gaskets and seals made of advanced composite materials are used that promise total tightness during the first years of the vehicle's life. However, the design of these seals often prioritizes the reduction of friction and lightness over extreme longevity. It is a documented phenomenon that highly prestigious brands present oil leaks through the valve cover gasket or the main crankshaft seal much earlier than their competitors. The technical reason is usually linked to the chemical composition of the elastomers used, which tend to harden and lose their sealing capacity due to the extreme heat generated by the turbochargers often located at the top of the engine in the famous Hot V configuration. A small oil leak in a European car rarely stays just a spot on the garage floor. Due to the compact engine layout, that oil usually drips directly onto coolant hoses or electrical connectors, degrading them and causing much more serious secondary failures. It is a chain of events where a small weakness in a rubber seal ends up compromising the integrity of vital systems. Reason 9. Infotainment systems and fiber optics in luxury models. The sophistication of a European cabin is not limited to the quality of its leathers or the fit of its panels, but to the complexity of its internal communication network. Unlike conventional systems that use copper cables to transmit audio and data signals, many high-end manufacturers adopted the Media-Oriented Systems Transport System, commonly known as the MOST bus. This system uses fiber optic cables to move large volumes of data between the navigator, the amplifier, the disc changer, and the telephone module. While this technology allows for unmatched sound quality and superior transfer speed, it is extremely fragile. Fiber optics work through light pulses that travel through polymer or glass filaments. If one of these cables bends slightly more than it should, or if a module in the circular network fails, the entire chain breaks. This means that if the satellite radio module burns out due to a small moisture leak, the owner will lose not only the radio, but also the navigation, the backup camera, and all vehicle warning sounds. Diagnosis of these faults requires optical bypass tools and specialized knowledge that few independent workshops possess, turning a peripheral component failure into a total blackout of the infotainment system that can cost thousands of euros to resolve. Reason 8. Component integration and mechanical accessibility. A fundamental principle of contemporary European engineering is compact packaging. In their quest to maximize cabin space and improve safety in the event of a collision, engineers design the engine compartment so that every square millimeter is occupied. This results in component integration that is a maintenance nightmare. It is common to find models where, to replace a xenon bulb or a simple coolant temperature sensor, the service manual requires the complete disassembly of the front bumper, the headlights, and even the front reinforcement. What in a vehicle designed under premises of simplicity would take 15 minutes and basic tools, in a European car can require 4 hours of specialized labor. This lack of accessibility not only makes preventive repairs more expensive, but also discourages correct maintenance by owners. When the cost of labor far exceeds the cost of the part, the vehicle begins to suffer technical neglect that ends in major failures, simply because changing a €10 hose required lowering the entire engine or removing the transmission. Reason 7. Comfort electronics and the proliferation of control modules. In the European vision of luxury, nothing should be left to chance or be operated purely mechanically. Every function in the cabin, from seat movement to ambient lighting intensity or soft door closing, has its own dedicated brain or control module. In a modern luxury sedan, it is possible to find more than 70 electronic control units communicating with each other. This architecture creates a network of mutual dependence where the failure of a comfort module in the rear door can, theoretically, interfere with the data network and cause errors on the instrument panel. These modules are usually located in vulnerable places, such as under the seats or in the sides of the trunk, where any water entry from a clogged sunroof drain can cause a massive short circuit. The problem is worsened because these components are usually linked to the vehicle's chassis number for security reasons, which prevents the use of scrap parts without a complex and expensive reprogramming process that can only be done with factory software. Reason 6. Air suspension systems and adaptive damping. The search for the magic carpet has been an obsession for brands like Mercedes-Benz, BMW, and Audi for decades. The result is air suspension, a system that replaces traditional steel springs with pressurized air-filled reinforced rubber bags. While the comfort is unmatched, the long-term maintenance cost is astronomical. Unlike a conventional shock absorber that can last 150,000 kilometers with gradual degradation, pneumatic components fail catastrophically. The airbags are exposed to the elements, engine heat and road dirt, causing the rubber to crack over time. A small air leak forces the electric compressor to work continuously to maintain the vehicle height, which inevitably ends up burning out the compressor motor. The owner then finds themselves with a double bill: replacement of the air springs and the compressor. Additionally, these systems integrate level sensors at each wheel and valve blocks that manage air distribution. A single failure in a position sensor can cause the car to lean dangerously to one side or drop completely to the bump stops, leaving the vehicle inoperable. In the second-hand market, it is common for the cost of repairing the air suspension to represent half of the total value of the car, leading many owners to perform mediocre conversions to steel springs, destroying the original driving dynamics of the vehicle. Reason 5. Engine thermal management and composite materials. In modern European engineering, the engine must reach its operating temperature as quickly as possible to reduce polluting emissions. To achieve this, manufacturers have abandoned robust, belt-driven metal water pumps in favor of intelligent electric water pumps and thermostat housings made of composite materials or high-resistance plastics. The problem lies in the fact that these plastic materials are subject to constant cycles of thermal expansion and contraction. Over the years, the plastic becomes brittle and develops microcracks that result in coolant leaks that are difficult to detect. Electric water pumps, although efficient because they can continue cooling the engine even after turning it off, have internal electronic components that fail without warning. Unlike a mechanical pump that usually warns with a bearing noise or a slow drip, an electric pump simply stops spinning, causing critical overheating in a matter of seconds. The complexity skyrockets with electronic thermostats, which are no longer simple wax valves, but actuators managed by the computer that decide the exact flow of coolant. If the connector of one of these sensors fails due to corrosion from a small leak, the computer can go into protection mode, limiting engine power and forcing a repair that involves disassembling much of the intake just to access a plastic part that has reached the end of its short, useful life. Reason 4. Ecological wiring and environmental vulnerability. Starting in the late 1990s and early 2000s, driven by European environmental regulations, many manufacturers began using wire insulation made from biodegradable materials, often based on soy derivatives or recyclable materials. What was in theory a step toward sustainability became a reliability disaster. These insulators tend to disintegrate over time due to heat accumulated in the engine bay, leaving the copper wires exposed. The result is a nightmare of intermittent short circuits and communication failures on the data bus that are almost impossible to diagnose without stripping the entire wiring harness. Additionally, it has been discovered that these organic materials are extremely attractive to rodents. In many regions, European vehicle owners find that rats or mice have chewed through critical sections of the main wiring, attracted by the smell and chemical composition of the insulation. A repair of this type can require full replacement of the vehicle's electrical harness, a task that can exceed 100 hours of labor and often ends in the total loss of the vehicle by insurance companies. It is a technical irony that the effort to make a car more ecological ends up causing the vehicle to become scrap much earlier than expected due to a wiring design that biodegrades while the car is still in use. Reason 3. Double clutch transmissions and the mechatronic unit. The promise of instantaneous gear changes and superior fuel efficiency led to the massive adoption of double-clutch transmissions, such as Volkswagen's DSG or BMW's DKG. These systems are, in essence, two manual transmissions within a single housing, managed by a complex electro-hydraulic system called a mechatronic unit. The heart of the problem is precisely this mechatronic unit, which combines electronic sensors and hydraulic actuators submerged in transmission oil. Extreme heat and the accumulation of fine metal particles resulting from natural clutch wear can contaminate the fluid and cause failures in the solenoid valves. When the mechatronics fail, the transmission usually loses even or odd gears or directly stops applying traction, leaving the driver stranded. Furthermore, maintenance of these boxes is critical and expensive. Ignoring the fluid and filter change every 60,000 kilometers is a death sentence for the system. Unlike a conventional automatic transmission with a torque converter, which is more tolerant of abuse, the double clutch is a piece of precision engineering that does not forgive negligence. Repairing a mechatronic unit or replacing the double clutch pack requires specific calibration tools and advanced diagnostic software, eliminating any possibility of cheap repair in general workshops. Reason 2. Extended maintenance intervals. The myth of 30,000 kilometer oil. One of the most damaging tactics for mechanical longevity has been the introduction of extremely long service intervals, promoted by marketing departments to reduce the apparent cost of ownership during the first years. Owners' manuals began to suggest that an engine could safely run on the same oil for 30,000 kilometers or 2 years. Under laboratory conditions or on highways at constant temperatures, this might be theoretically possible, but in the real world, with cold starts, short trips and variable climates, the oil degrades much earlier. The lubricant loses its viscosity properties and its detergent additives become saturated, leading to the formation of sludge and carbon deposits on critical components. Turbocharged engines suffer the most, as degraded oil carbonizes inside the turbo feed lines, clogging the flow and causing premature turbine failures that cost thousands of dollars. Additionally, timing chain tensioners, which depend on clean oil pressure to function correctly, begin to fail, allowing the chain to stretch and, in the worst case, skip a tooth, destroying the valves and pistons. This policy of extended maintenance is a programmed death sentence that usually executes just after the factory warranty expires. Reason 1. The lease philosophy designed to shine the first 3 years. The business model of European premium brands has mutated toward a lease economy. Engineers are no longer commissioned to build a car that lasts 20 years as in the era of the Mercedes-Benz W124. Now the goal is for the vehicle to be perfect during the first 36 or 48 months. This allows the use of materials that have an exceptional look and feel when they are new, but lack long-term durability. Soft-touch plastics that become sticky in the sun, adhesives that come loose, and electronic components with a useful life calculated to barely exceed the warranty period. A modern European car is a masterpiece of programmed obsolescence. The first owner enjoys an unsurpassed technological experience, but the second or third owner inherits a financial time bomb. The complexity of the driver assistance systems and internal communication networks are designed with such a level of integration that the failure of an aesthetic or comfort component can disable vital safety functions, forcing the user to get rid of the car because the cost of repair exceeds the market value of the vehicle. So, is it a lack of quality or an excess of technology? The big question that haunts enthusiasts is whether European reliability has fallen due to negligence or ambition. The reality is a mixture of both. It is not that German or Italian engineers have forgotten how to manufacture robust parts, but that they have decided to prioritize performance, extreme efficiency, and technological integration over simplicity and strength. Every gram of weight saved through the use of plastics instead of aluminum, and every milliliter of fuel saved through ultra-high pressure injection systems adds a layer of fragility. We are facing an excess of engineering where there are too many possible points of failure. A modern car has more lines of code than a fighter jet, and more sensors than a space station. This technological density makes the statistical probability of something failing exponentially higher than in a vehicle designed with proven mechanical solutions. Perceived quality is higher than ever, but long-term mechanical integrity has been sacrificed on the altar of sales figures and government regulations.